Welcome to The Deep Dive, the show where we take a stack of the latest research and distill it into the most important nuggets of knowledge and insight just for you.
Glad to be diving in.
Today, we're tackling a fundamental challenge in artificial intelligence that really throws into sharp relief the remarkable difference between how humans learn and how machines learn.
Yeah, it's fascinating.
Think about it for a moment. When you pick up a new game, maybe a board game, maybe a video game, how long does it take you to really grasp the core mechanics?
Usually just a few minutes, right?
Exactly. The rules, the objects, how they move, how they interact. Probably just minutes. You sort of intuitively understand that a ball bounces, a character walks on the ground. Objects don't just vanish into thin air unless, the game explicitly tells you they do. You build this mental model almost instantly.
It's a really fascinating aspect of human cognition, isn't it? We're just
Yeah.
incredibly adept at quickly forming this coherent internal model of our environment. It's physics, even in totally new situations.
Right.
And it's not magic. We leverage what cognitive scientists call core priors, these fundamental, almost innate assumptions about how the world generally works.
Like a foundation for learning.
Precisely. They provide this foundational scaffold for all new learning.
Okay, so now contrast that with the state-of-the-art in traditional AI, especially in deep reinforcement learning.
Yeah, the difference is pretty stark.
Often, these incredibly powerful models, they need millions of interactions, massive data sets, huge amounts of training time, sometimes weeks or months of simulated gameplay,
Just to get started.
just to begin understanding the basic rules of a relatively simple environment. Imagine if an AI could just bypass that immense data hunger, learn complex game dynamics in mere minutes, almost as fast as a human child.
That sounds like a huge leap.
It does. But today, we're diving into a groundbreaking new architecture that aims to do just that.
And what's really interesting here is that this data hunger you mentioned, in current deep reinforcement learning, it's probably the biggest bottleneck for actually using AI in the real world.
Because data isn't always cheap or plentiful.
Exactly. Data can be sparse or really expensive to acquire. And it's precisely this core problem that the research we're looking at today, called AXIOM, is trying to solve.
Okay, let's unpack this. AXIM. It stands for Active Expanding Inference with Object-Centric Models.
Quite a mouthful, but descriptive.
It represents a groundbreaking new architecture. The promise is bridging this colossal gap in data efficiency by taking a fundamentally different approach to how AI sees and understands its world.
And connecting this to the bigger picture, AXIOM isn't just aiming for data efficiency. It's also aiming for a level of interpretability.
Ah, the black box problem.
Exactly. Interpretability that's often completely missing in many modern AI models. And it gets there by leveraging this minimal yet very expressive set of core priors about objects and how they interact.
So like the human learning we talked about.
Surprisingly similar, yes. It's a real departure from the purely data-driven sort of blank slate approach that's dominated deep learning for a while.
So, our mission for this deep dive is to explore exactly how AXIOM pulls this off. We'll dissect its technical components, look at its performance against the current state of the art,
And see how it stacks up.
and, most importantly, understand what this could mean for the future of AI learning. Especially in situations where you need rapid adaptation and understanding, our goal is to give you that shortcut to being well-informed on this cutting-edge stuff.
And the source for our discussion today is a really insightful research paper. It's titled AXIOM, Learning to Play Games in Minutes with Expanding Object-Centric Models. A very compelling read.
All right, let's get right into the heart of the problem AXIOM tackles, this pervasive issue of data overload and reinforcement learning. DRL, deep reinforcement learning, it's had some truly incredible, almost cinematic successes recently, right?
Oh, absolutely. We've all seen the headlines.
We've marveled as models like DeepMind's AlphaGo conquered Go, a game once thought, purely human territory.
Or AlphaStar mastering StarCraft 2. The complexity there is just immense.
These achievements are undeniably monumental. They show the raw power of these algorithms when you give them enough resources.
Definitely. The achievements are undeniable, pushing the boundaries of AI in complex, structured environments. But, and this is a big but, these successes come with significant drawbacks, often overlooked.
What data cost?
Primarily, yes. DRL typically requires truly massive amounts of training data. We're talking often millions, sometimes even billions of interactions with the environment to get good.
Which means you need huge storage, too.
Exactly. It necessitates using large replay buffers to store past experiences. It's basically a huge memory bank the AI keeps sampling from. And the learning itself often just focuses purely on maximizing reward.
Like a score.
Right, maximize the score, which can lead to a brute force approach, lacking structured exploration of the environment itself. The AI just tries things over and over until it stumbles onto what works.
The try everything method.
Yeah, this explore everything until it sticks approach. It works sometimes, but it's fundamentally far from efficient or, frankly, elegant.
And that's where human learning just seems so much more effective as a blueprint. You know, we humans, we generalize rapidly to new tasks because we don't start from zero.
We have that built-in foundation.
We come pre-equipped, in a sense, with what this paper and cognitive science calls core priors or hyper priors. Like, our brains have a preloaded OS with some basic understanding of how things work. Can you elaborate a bit more on what these core priors really are? Give us some concrete examples.
Certainly. Core priors are these fundamental organizational principles. They shape our perception, our cognition, ultimately our learning. They're not just vague guesses. They're deeply ingrained insights that let us make sense of the world quickly.
Without relearning physics every morning.
Exactly. We don't have to relearn basic physics or causality from scratch every time. For instance, object permanence. We intuitively know an object still exists, even if we can't see it.
Right. Peekaboo relies on that.
Precisely. We understand objects follow smooth trajectories unless some external force intervenes. A collision, friction, gravity. Think about a kid playing with blocks.
They figure it out fast.
Very fast. They push a block, it moves. They let go of a ball, it falls down. These are all core priors in action. We implicitly grasp action-consequence relationships for causal reasoning. Hit a drum, makes a sound. Turn a knob, something changes.
But standard DRL doesn't have this.
Typically, no. Traditional DRL without these priors baked in often have to discover these basic physics and causal links from scratch for every single new task. It burns through vast amounts of data just to build a rudimentary world model that humans kind of get for free.
So if DRL is starting from absolute zero, AXIOM gets this massive head start by baking in these fundamental understandings.
That's the core idea.
And that's where the active inference framework comes in, isn't it? It sounds like a really natural fit for incorporating these prior beliefs, like an AI learning like a scientist, forming hypotheses and testing them.
That's an excellent question, and it brings us right to active inference. It's a principled Bayesian framework, and it naturally incorporates prior knowledge. What's really crucial about active inference is that it doesn't just learn a world model.
It does more.
It also continually quantifies its own uncertainty about its beliefs and predictions. This theoretical elegance, and how closely it seems to align with human cognition constantly predicting, updating, makes it very appealing.
So it's not just reacting.
Right. The agent isn't just reacting to stimuli. It generates predictions about what it expects to perceive, and then actively tries to resolve discrepancies, the differences between prediction and reality.
But it hasn't scaled well historically.
That's been the catch. Historically, active inference models have been mostly confined to relatively small-scale tasks, and they often required custom-designed priors for each specific domain. They generally lack the versatility and generalization we see in DRL across diverse, complex tasks like video games or robotics.
So they weren't flexible enough.
Exactly. This inability to scale and generalize easily has been a significant hurdle for active inference.
Which brings us right back to AXIOM. This paper is tackling that exact challenge, scaling active inference, bridging that gap with DRL. What's AXIOM's core idea for doing this? How does it actually integrate these things?
AXIOM proposes a genuinely novel active inference architecture. It directly integrates a minimal but really expressive set of core priors, specifically about objects and their interactions, right into the learning process itself.
Okay.
The key insight here is that it's designed to bring together the data efficiency and the inherent interpretability you get from Bayesian approaches,
The best of that world.
while also achieving the broad, across-task generalization that's been the strong suit of DRL. So unlike older active inference models needing hand-engineered priors for each task, AXIOM offers a more general framework for applying these human-like insights.
Getting the best of both worlds.
That's the goal,
So instead of just processing raw pixels like an undifferentiated mess,
which is often how DRL agents see things.
AXIOM starts with the basic built-in understanding that there are distinct objects in the world. How does it represent these complex visual scenes efficiently using these priors?
Fundamentally, AXIOM represents scenes not as that monolithic array of pixels, but as compositions of distinct, separable objects. This object-centric view is a crucial departure.
Seeing objects, not just colors.
Precisely.
Yeah.
And its internal model for how objects move is built on a very specific, efficient assumption.
Yeah.
They follow piecewise linear trajectories.
Piecewise linear, like straight lines until something happens.
Exactly. Imagine billiards. A ball moves straight until it hits another ball or the cushion, and its trajectory changes predictably. AXIOM's model inherently bakes in this kind of basic physics prior.
So it doesn't have to learn Newton's laws from scratch.
Effectively, yes. It captures sparse object interactions efficiently without needing to relearn basic mechanics every time. This dramatically cuts down the data needed to understand movement and collisions.
And it's not a fixed model, right? It
Yeah.
sounds like it's constantly adapting, refining, maybe even simplifying its understanding as it learns. That feels very intelligent.
Precisely. AXIOM's generative model structure is designed to be highly adaptive. It expands online. As it sees new data, new objects, new interactions, it dynamically grows, learning new mixture models from single events.
But it doesn't just get more complex.
No, and this is key, it's also periodically refined through a process called Bayesian model reduction, or BMR.
BMR. Okay.
This BMR step is absolutely crucial. It helps induce generalization by actively finding and merging redundant model components. It simplifies the model structure.
So it cleans itself up.
You could think of it that way. It's a continuous cycle. Learn new patterns, then simplify the internal representation to stay efficient and generalize better, like pruning unnecessary branches on a tree to keep it strong. Focus on the essential knowledge.
Okay, let's really get into AXIOM's architecture now. The paper describes it as having 3 pillars and an identity, all driven by this core principle. It starts with the generative model and this concept of free energy, right? That feels central.
Yes, you've hit a key point. At its core, AXIOM learns its object-centric state space model by maximizing Bayesian model evidence. That's a rigorous way of saying it's trying to find the best possible internal model to explain what it sees.
Makes sense.
And crucially, maximizing this evidence is mathematically the same as minimizing something called expected free energy through active interaction with the world. This isn't just jargon, it's the fundamental driving force, the engine of active inference.
So it's not just trying to predict what's next accurately, but it's also trying to learn what it doesn't know. That sounds like a powerful way to drive exploration, almost like curiosity.
Exactly. Imagine your brain constantly predicting the world, then comparing those predictions to reality. Expected free energy measures the surprise or mismatch between expectation and observation. By minimizing it, AXIOM isn't just aiming for accurate predictions.
It's seeking knowledge.
It's actively seeking out situations that will reduce its future uncertainty. This fundamentally drives its intelligent exploration. It prioritizes gathering info about the unknown parts of its world model, not just blindly chasing immediate rewards.
That's elegant.
And it neatly factorizes perception and dynamics into separate components, allowing for more targeted learning.
Okay, so that's the driving principle. The first pillar is the slot mixture model, or SMM. What does that do with the raw visual data? How does it actually slice up a scene into objects?
The SMM is AXIOM's perception module. Think of it as its eyes on the pixel world. Its main job is to take that raw visual input, the stream of pixels from the gain screen, and parse it into distinct object-centric representations, or what they call slots.
So it sees a paddle, a ball, a block, not just colored pixels.
Exactly. Instead of a jumble of undifferentiated colors and shapes, it immediately recognizes separate entities. It's a foundational step, shifting the AI's view from pixel level to object level.
So in a simple game like, say, Breakout with paddle, ball, blocks, the SMM would identify each of those as a distinct thing.
Precisely. It operates as a Gaussian mixture model, which is a statistical model good for finding subpopulations. Here, it dynamically expands to handle new objects it encounters. Each pixel gets assigned a probability belonging to one of k possible slots, representing different objects.
And for each slot, it figures out details.
Yes. For each identified slot, the SMM infers continuous latent variables describing the object. Its 2D position, p, 2D velocity, v, color, c, shape encoded as spatial extent, e.
Latent variables, hidden properties it inferred.
Right. And even an unused counter to track how long a slot's been inactive, which is useful for predicting if something left the screen and might come back.
So looking at figure 1 in the paper, with the yellow paddle, red square, green block, the SMM breaks those down. And those abstract visuals in figures 1A and 1E, the circles and ellipses showing inferred position, color, shape, that's the SMM's output visually.
That's exactly right. Those visuals are a direct output of the SMM's inference. It's a human-readable picture of how it abstracts dense pixels into meaningful, distinct object concepts, a crucial first step for everything else.
Okay, SMM finds the objects. Then the next piece is the identity mixture model, or IMM. What's its specific job? Why is identity so important here?
Right, so once the SMM identifies objects and extracts their continuous features like color and shape, the IMM steps in. It infers a discrete identity code for each object. And this identity is absolutely critical for generalization.
How so?
Think of it like this. Imagine a game with 5 identical red balls. A traditional system might learn 5 separate models for how each ball moves. Hugely inefficient.
Yeah, that seems redundant.
The IMM, however, allows AXIOM to use the same underlying dynamics model across similar objects.
Ah! So if it learns how one ball bounces or reacts to being hit, it applies that knowledge to all the balls, regardless of which specific one it is.
Exactly. That's a powerful form of type-specific learning. It massively improves data efficiency because knowledge from one instance generalizes immediately to all others of that type.
And it helps if things change.
Yes, it also allows for remapping identities if things like object colors or shapes suddenly change mid-game. The IMM provides a robust way to categorize and recognize objects based on their core features, even if superficial looks shift. We'll see later how that helps with robustness.
Okay, perception, SMM, identity, IMM. Now we get to the core dynamics with the transition mixture model, the TMM. How does this model the actual movement and interactions?
The TMM is where the system really learns the dynamics, the physics of each object. Its main function is discovering motion prototypes, distinct, recurring patterns of movement.
Like falling or sliding.
Exactly. Falling due to gravity, sliding on a surface, bouncing off a wall, being propelled. It's formulated as a switching linear dynamical system, or SLDS.
SLDS, okay.
This means for any object, the TMM's switch variable picks one of several possible sets of linear parameters to describe that object's trajectory right now.
So instead of one super complex function for all movement, it learns simpler linear motion building blocks and just switches between them. That sounds much more efficient.
It is very efficient, and here's the really crucial part. These L-transition components, these motion prototypes, they're shared and learned across all K object slots.
Shared, meaning?
Meaning, a single falling prototype can explain the motion of any falling object in the game, regardless of its identity, color, or which slot it's in. It learns these fundamental kinematic rules once and applies them broadly.
It's like distilling the basic physics of the game world into reusable parts.
Precisely. Interpretable, reusable components.
That's really cool. It learns the physics, applies it everywhere. Okay, the final piece, bringing it all together, the recurrent mixture model, the RMM. This is where it learns about object interactions, right? Like the ball hitting the paddle or collecting a coin.
Yes, the RMM is where AXIOM builds its understanding of how objects interact with each other and, crucially, how the agent's actions influence the world. Its function is to infer the switch states of the TMM, which motion prototype is active directly from the current object-level features.
So it connects the dots.
It does. It's a sophisticated module. It models the distribution of both continuous features, position, velocity, and really important interaction features, both the distance to the closest interacting object, and discrete features, like the object's identity code from the IMM, the TMM switch state itself, the action the agent just took, and the reward received.
So the RMM is basically learning a complex causal map.
Yeah.
If I do this, or if object A is near object B, then object B will likely switch to that motion state.
Precisely. It allows the RMM to learn how actions, rewards, and the states of other objects influence an object's motion. This directly maps to that object interactions flow shown in Figure 1 of the paper. This is where it learns, say, pressing jump near a platform leads to upward motion, or a ball reverses direction when hitting the paddle.
And it filters things, too, to stay focused.
Yes, it uses auxiliary discrete variables like presence, is the object on screen, and moving is actually moving, to intelligently filter which slots the RMM actively learns from.
Focusing computation.
Exactly, focusing resources only on relevant active elements. And that unused counter from the SMM also helps the RMM predict when objects might reappear or become important again.
This architecture is intricate, but seems really logical. Okay, let's talk payoff. What are the practical benefits? The paper highlights unprecedented efficiency cry-offs. Walk us through those, starting with maybe the most critical one, sample efficiency.
The efficiency gains are really compelling, a major leap. First, as you said, sample efficiency. AXIOM learns sequentially, frame by frame, processing observations as they come in.
No big memory bank.
Right. It eliminates the need for those large replay buffers, common in DRL. Replay buffers eat memory and can make it hard for an agent to adapt quickly if the environment changes, because it's always sampling from old data.
But AXIOM adapts on the fly.
Yes, it's online, Sequential learning allows for rapid adaptation to changing conditions, much more like how a human learns. You don't store every single moment of your life to learn something new. You process it in real time.
Okay, so less data needed overall and faster adaptation. What about the actual computing power required?
That's computational efficiency, another huge plus. AXIOM performs variational Bayesian updating, and this is really key. It does not rely on gradient-based optimization.
No gradients. That's rare in modern AI.
It's a major departure. Think of gradient methods common in deep learning, like carefully calculating the slope and taking tiny, expensive steps down a hill. Variational Bayesian methods, crudely speaking, let AXIOM directly update its beliefs by fitting a simpler approximation to the complex reality. It's mathematically sound and avoids the heavy computation of backpropagation through deep nets.
And the numbers back this up.
Significantly. Look at Table 2 in the paper. AXIOM's parameter count is tiny, 0.3 to 1.6 million. Its model update time, a swift 18 milliseconds plus or minus 3 per step.
Wow. And the comparison.
Compare that to baselines. BBF, 6.47 million parameters, 135 milliseconds per update step. Dreamer v3, a massive 420 million parameters, taking 221 milliseconds per update.
Orders of magnitude difference.
Yes. Now, AXIOM does have some planning overhead, but the core model update itself is far, far more efficient.
That's incredible. What allows it to learn the structure of the environment so quickly then? Is that the fast structure learning part?
It absolutely is. AXIOM's mixture architecture, with its dynamic component adding and that Bayesian model reduction we talked about, facilitates extremely rapid learning of the environment structure.
It grows and shrinks as needed.
Exactly. It doesn't start fixed. It adds new mixture components when needed, new object, new interaction. And conversely, BMR merges redundant components, simplifying the model, boosting generalization. This dynamic adaptability is core to its speed. It builds a minimal sufficient model.
Okay, efficiency covered. What about exploration? How does active inference help it explore smarter? That's the uncertainty-aware exploration, right?
Yes, AXIOM's policy selection, how it decides what to do next, is uniquely augmented with information-seeking objectives.
So it's not just about score.
Not just immediate reward, like a greedy agent just trying to max the score right now. It also actively seeks out and explores states that are expected to reduce its uncertainty about the environment.
Like being curious.
Very much like curiosity. If it's unsure how a new object works, or what happens over there, it prioritizes exploring those areas to gain knowledge, even if there's no immediate reward. This intelligent, curiosity-driven exploration leads to more robust and much faster learning overall. It prioritizes filling gaps in its world model.
This sounds like a massive step towards understanding what the AI is actually doing, moving beyond these opaque black box models. This interpretability aspect seems like a huge feature.
It absolutely is. Maybe one of AXIOM's most profound contributions.
Yeah.
Unlike many DRL methods learning inscrutable patterns in giant neural nets, AXIOM builds this structured, object-centric model. Its latent variables, its parameters, are directly interpretable in human terms.
A game changer for trust and debugging.
Definitely.
So we can actually peek inside and see what the AI is thinking in a sense, not just the final action, but its model of reality.
Yes, to a remarkable degree. AXIOM's inferred latent variables directly correspond to concepts we understand. Object shape, color, position. If you look at Figure 4a in the paper, the middle panel for the impact game, you can see these imagined trajectories in AXIOM's latent space. They are directly readable in terms of object colors and positions. You can literally trace how the AI envisions a ball moving, bouncing, complete with its color and location. It's not just predicting pixels, it's predicting the behavior of conceptual objects. That level of insight is almost unprecedented.
That is incredibly powerful. It's a conceptual understanding, not just pattern matching. And the TMM breaking down motion into those simpler linear prototypes, that must also help understanding.
Exactly. You can see the distinct motion prototypes. It's learned bouncing, falling, and how it switches between them to describe complex movement. Plus, AXIOM offers remarkable reward mapping.
Reward mapping.
The RMM's clusters can be visualized in space. They clearly show where AXIOM expects rewards, green clusters in the paper, or punishments, red clusters. Again, Figure 4a for impact vividly shows red clusters at the bottom where it expects punishment if it misses the ball. This transparency lets us see its learned associations, its beliefs about rewards, directly. No reverse engineering needed.
And that Bayesian model reduction, BMR, it helps interpretability too, by simplifying, not just for efficiency.
Indeed. Figure 4b clearly shows BMR merging clusters, reducing the number of active RMM components during training. like in the Explode game. This isn't just efficiency, it reveals the minimal set of dynamics needed for good performance. It shows the essential, distilled rules the AI learned, makes its decision process transparent and efficient, trimming the fat to get the core truths.
Okay, to really prove these capabilities, especially against standard DRL, the researchers created a new benchmark, Game World 10K. What is this testing ground and why did they need a new one?
Game World 10K is a new, carefully designed set of 10 pixel-based environments. It was specifically made to test how efficiently an agent learns different games within a very tight budget, just 10,000 interaction steps.
10,000, that's tiny compared to the millions DRL often uses.
Exactly, that's the point. Figure 2 shows the games. AB8, Spaceship, Bounce, Paddleball, Cross, Navigation, Drive Racing, Explode, Fruits, Gold, Hunt, Impact like Breakout, and Jump, Platformer.
They look simpler visually than, say, Atari games. What was the design thinking there? Why simplify the visuals?
That's a great question. Gets to the core purpose. The philosophy was to simplify the visual elements, usually single-color sprites, different shape sizes, to focus explicitly on the representational mechanisms. How does the AI model dynamics and control? Not how good is it at complex image segmentation.
So less visual noise, more focus on the internal model.
Precisely. Unlike benchmarks like Atari, ALE, or Mujoko that stress long-term planning or visual complexity, Game World 10K simplifies visuals. The games are explicitly object-focused, continuous trajectories, sparse interactions solvable by humans in minutes. This setup lets researchers zero in on how the AI builds its world model, not just its image recognition skill.
And critically, Game World allows for controlled interventions. That sounds powerful for testing real understanding, not just memorization.
Absolutely, a key feature. It allows precise control over game features. Researchers can run systematic tests, introduce sparse, sudden changes mid-game, change an object's color, change its shape at a specific training step.
Like pulling the rug out from under it?
Sort of. It directly tests how adaptable and robust the AI's internal model is when its world suddenly shifts, mimicking real-world unpredictability.
Okay, moment of truth time. Performance and robustness. The paper claims AXIOM has an uncontested edge, especially in these low-data situations. What do the actual results show against the DRL baselines?
The key quantitative finding is pretty stark. AXIOM gets higher, or at least comparable, average cumulative reward compared to state-of-the-art baselines like BBF and Dreamer v3 across every single game world environment.
Every single one?
Every one. And critically, within that tiny 10,000-step budget, which, again, is extremely low for DRL. For instance, in games like Bounce or Impact, AXIOM clearly wins. In others like AV8, it matches them but gets there much faster.
So it's not just about the final score. It's about how fast it learns and how little data it needs. That's the key for real-world use.
Exactly. AXIOM converges much, much faster, often hits most of its final reward within the first 5,000 steps, half the budget. The baselines, BBF and Dreamer v3, often need the full 10K steps just to catch up, and frequently don't even reach AXIOM's peak.
You can see that in the graphs.
Clearly. Figure 11a shows it well. AXIOM's green line often shoots up sharply and plateaus significantly higher than the red BBF and blue Dreamer v3 lines.
Right.
It's powerful visual validation of its sample efficiency. And remember, this is all achieved without gradient-based optimization, a major technical feat showing an alternative path.
That's impressive, especially given how dominant gradients are. But games can change unexpectedly. How robust is AXIOM if, say, a character suddenly changes color or shape mid-game?
This is where AXIOM's interpretable structure really pays off, showing deep understanding beyond just speed. They tested this systematically, perturbing game mechanics, changing object color or shape right at step 5,000, smack in the middle of training.
And did its performance tank?
Not really. AXIOM showed strong resilience to shape perturbations. Figure 11c shows this. Its identity model, the IMM, successfully re-infers the object type. It maps the new shape onto its existing identity.
So it realizes it's still a ball, just looks different.
Essentially, yes. It maintains performance because its concept of the object goes beyond just its look, linking to its type or function.
What about color changes? That seems trickier if color is a main identifier in these simple games.
You're right. Color changes can be challenging, especially if color is very distinct. Initially, a color change can cause a slight dip in AXIOM's performance. Figure 11b shows this. It might initially treat the recolored sprite as a new object with unknown dynamics.
But it recovers?
Yes, it recovers rapidly by relearning the dynamics for this new identity. But here's where the interpretability leads to something amazing. The color remapping trick.
Color remapping trick. That sounds like something you could only do if you knew exactly what the AI was thinking. Impossible with the black box.
Precisely. A fantastic example of interpretability enabling direct intervention. Because AXIOM's latent features are readable, it explicitly represents color and shape internally. The researchers could, during the color change experiment, turn off the influence of color on the IMM's identity decision.
Tell it to ignore the color.
Effectively, yes. Force it to use only shape information to identify the object. This remapping trick successfully linked the recolored objects back to their original learned dynamics. Performance drops were prevented entirely for some games. Figure 11.2 shows this dramatically.
Wow.
This isn't just a hack. It shows how interpretability allows direct debugging and enhancement, boosting robustness in a way impossible with opaque models, like fixing a specific wire instead of swapping the whole box.
That's a really strong case for interpretability having practical benefits, not just being nice to have. What else did the ablation studies reveal when they turned parts off?
The ablation studies gave crucial insights into what each part contributes. For instance, including that information gain term in planning the curiosity factor.
Yeah.
It generally helps agents learn faster in some games, like Bounce, by encouraging exploration of unknown states. But interestingly, it could sometimes hurt performance in others, like Gold or Cross.
Why would seeking information hurt?
If the information-rich states also happen to lead to punishment or negative rewards, exploring a new, dangerous area might teach you something. But if you die doing it, maybe it wasn't worth the immediate risk. Figure 7, purple line, and Figure 8b show this trade-off between exploration and exploitation clearly.
So curiosity needs context. What about Bayesian model reduction, BMR, turning that off?
BMR's impact was also nuanced. It was vital in games needing spatial generalization, like Goal and Hunt. Merging similar clusters clearly helped performance there. BMR let the model generalize dynamics across different locations.
And not always helpful.
Surprisingly, no. In Cross, disabling BMR actually improved performance slightly. Why? Because BMR in that case might have prematurely merged some distinct clusters, making the agent less likely to explore certain specific locations needed for high scores. Figure 7, orange line, and comparing figures 8a and 8c show this.
Interesting.
It raises fascinating questions about when and how to best apply BMR during learning. It's clearly important for generalization, but the timing is key. It's not a blunt instrument.
This all sounds incredibly promising, a path towards AI that learns faster, more transparently. But like any new tech, AXIOM must have limits currently. What are they, and what's the next big step?
You're absolutely right. Important to be realistic. AXIOM, as it stands, does have limitations. Those core priors making it so effective, object permanence, basic causality, they are still engineered. Humans provide these fundamental assumptions.
They don't emerge automatically.
Not yet. And AXIOM hasn't been deployed on really complex, visually diverse tasks like the full Atari suite or super open-ended worlds like Minecraft. In those domains, the underlying rules are less obvious, they're way more objects, and defining an object itself is much harder than in Game World 10K. That's a big step up in complexity.
So the human still provides the initial scaffolding. The ultimate goal, the next frontier, would be for the AI to discover those core priors itself, infer them from raw data without guidance.
Absolutely. That is, without doubt, the critical next step. Developing methods for AI to automatically infer these foundational principles directly from unstructured, real-world data. That would be a massive leap.
Letting it learn the absolute basics on its own.
Yes. It would allow approaches like AXIOM to tackle much more complex, open-ended problems without needing humans to explicitly engineer domain knowledge, moving from handcrafting intelligence towards true autonomous discovery. The ability to learn fundamentals from experience alone is a hallmark of biological intelligence.
And if we achieve that, what's the ultimate vision? What kind of AI could we build?
The vision is building truly adaptive agents. Agents that can rapidly construct structural models of entirely novel environments from scratch, fundamentally changing how quickly they grasp new tasks.
Closer to how we learn.
Significantly closer. Less brittle, needing far less data, vastly more capable in dynamic, unpredictable, real-world situations. Robotics, science, you name it. Imagine an AI entering any new situation, instantly grasping the underlying physics and causal rules, adapting its behavior without massive retraining. That's the promise.
So let's wrap this up. We've just explored AXIOM. It's a novel, fully Bayesian, object-centric agent. It shows superior sample efficiency, remarkable interpretability, strong robustness, all learning simple games from pixels.
And critically, without the usual suspect.
Right. No neural networks as we typically think of them, no gradient-based optimization, no big replay buffers techniques that are the bedrock of most current DRL. It really showcases the potential of blending human-like structured priors with powerful Bayesian methods.
It's a compelling argument for a different path, maybe a more biologically inspired one.
By building these structured, transparent world models, AXIOM hints at a future where AI learns with a tiny fraction of the data today's systems need. And the fact that you can understand its internal model, that opens up huge possibilities for debugging, collaboration, trust.
It moves us towards systems that don't just do tasks, but might actually understand the mechanisms of their world.
So here's something to think about. If an AI can now learn the basic physics and interactions of a new game in minutes, just by seeing objects and relationships, how might this fundamentally change AI design for complex real-world tasks? What problems beyond games become tractable when AI can spontaneously build compact, interpretable world models for rapid decision-making in messy, dynamic environments?
This approach, this blend of built-in structure and efficient learning, could be a crucial step. Maybe the crucial step towards truly intelligent adaptive agents that learn about the world as effortlessly and intuitively as we do.
It definitely points towards a more robust, generalizable kind of intelligence, capable of real causal reasoning, not just pattern matching. A really exciting possibility for the future, something profound to chew on.